Hello, my name is Franco Di Giovanni of Airzone 1 Limited, and I'm going to provide an introduction to technical aspects of air quality for environmental assessments. Just as a note to professionals listening to this, that if you have a learning credit requirement, this presentation may count towards that. For example, planners are required to gain continuous professional learning or CPL program credits, and engineers are also encouraged to record their peak program credits. Other professionals too may have similar requirements that this presentation may count for. Just a little bit about our own company. We're an employee-owned firm offering air quality services since 1979 in ambient air quality, monitoring and modeling, environmental assessments and reviews, land use compatibility assessments and reviews of assessments, permitting, ECAs and EASAs, and emissions reporting, MPRI, TRA and Chemtrack, and also indoor air quality and OH&S. And we have our own CALA accredited laboratory where we analyze many of the samples that we collect. Just to give you some idea of our previous assessment experience, we worked for proponents in waste-to-energy facilities, the oil sands, metal extraction processing plants in Canada, cruise terminal expansions, landfill establishments and expansions. We are also an MTO RACS qualified air quality consultant within Ontario. We've also worked for stakeholders or opponents. For example, recently we peer-reviewed terms of reference for a provincial, for a landfill that's being assessed under a provincial EA. In terms of our review experience, we've done reviews for municipalities under 4 EAs, for wastewater treatment plants, for the town of Oakville, for the Trans-Canada gas plant. We've also conducted reviews for other jurisdictions. For example, we conducted a review for the federal government for the Highway 427 extension, and we've done reviews for international bodies such as the World Bank, where, for example, recently we've reviewed an air quality assessment for a proposed lignite plant in Eastern Europe. So much of this presentation is based on the International Association of Impact Assessments Guide to Air Quality Assessment. This is published on the IAIA website in the spring of 2017, and I was the primary author. It's freely available as a downloadable PDF on the IAIA website if you wish to have a copy. Just as a jurisdictional disclaimer, it is important that the audience understand that this presentation provides guiding principles only and not detailed regulatory or technical advice. In particular cases, the audience are advised to check with the project legal jurisdiction to obtain any specific requirements set forth for their EA. Air quality is, or should be, a central focus of many EAs where significant air contaminants may be emitted from the proposed development. What we're aiming to do here, as reflected in the IA guide, is to provide guidance in areas of uncertainty and inappropriate air impact assessment methods that have been applied in the past. To set the framework for air quality assessments, it is generally required to estimate worst-case impacts on air quality by estimating worst-case emissions combined with worst-case meteorology, because it answers the basic question, what are the worst effects of this project in the surrounding community? For example, coal crushing machinery in an open cast mine or at a power plant may emit dust to the environment. The more coal processed in a day, the greater the dust emissions from that machinery, and so maximal production and therefore dust emissions and impacts are of concern. I've included the term maximal to describe emissions in quotes to emphasize the fact that it may not always be the operating scenario with the greatest emission rate of a source that causes the highest off-site air quality impacts. For example, a gravel pit may have the greatest site-wide dust emissions while crushing gravel at a central operating plant, but the highest off-site impacts on air quality may only occur when extraction operations occur near the peripheries of the extraction zone, close to off-site residences. Worst-case impacts must be considered separately for each contaminant emitted, as separate air quality standards apply to different contaminants, and maximal operating scenarios may differ for different operations emitting different contaminants. The initial stages of an EA, and often the most crucial, are when project scoping and terms of reference are formulated. Most of the time, these terms of reference are subject to public review and agreement before the assessment is begun. The need at this early stage is to correctly identify all sources of air emissions related to the project. These are termed subject sources. Subject sources can be on or off-site as long as they relate to the project. For example, including the impacts of truck emissions carrying products from a proposed rail intermodal hub would be defined as off-site subject sources. In turn, these subject sources release contaminants which, for the EA, become the contaminants of potential concern, or COPCs for short. Once these have been identified, then non-subject sources of these same contaminants must also be considered, as will be mentioned later. As with other contaminant releases to the environment, air quality assessments must begin by considering emission sources, their dispersion into the environment, and their eventual effects on air quality levels at receptors of interest. So, starting with project emissions, it's obviously important to identify all actual or potential sources of air emissions. Reviewers, if you're a proponent, must be convinced that all sources have been included in your study. Once sources have been identified, the next step is to identify all contaminants emitted by those sources. This may be relatively straightforward when you have a common source of air emissions, for example, natural gas combustion, which has been heavily characterized in the past, but it may be more of a challenge when the source is a novel process or a fairly unique process, and there's not a lot of background data on the emissions from these types of sources. A common error occurs when considering fugitive dust or dusts in general, where speciation is necessary but is often not done even when road dusts that may contain, often with road dusts that may contain potentially harmful substances like crystalline silica. These identified contaminants then, of course, as mentioned earlier, become the COPCs or contaminants of potential concern for the project. It is also important to account for spatial and temporal variability in emissions from subject sources, or, where appropriate, simplifying assumptions can be made. In the example of dust emissions from mining activities in an open cast mine, the location of mobile mining machinery, as close as permissible or likely possible to property boundaries, must be assessed if it is allowed and intended to move to those locations during excavation. Alternatively, management may impose their own siting limitations on mobile machinery to ensure that dust emissions are suitably mitigated by distance dilution, for example. The next step is to quantify the emission rates for each contaminant from each source. Here I'm not going to expand on the usual methods described in detail elsewhere, for example, source testing, emission factors, mass balance techniques, etc. After emissions have been characterized, the next step is to predict the dispersion of these contaminants from the sources to sensitive locations in the community. One way to determine airborne pollutant levels resulting from emissions from subject sources would be to measure the levels of all substances emitted to the surrounding community. However, actual measurements will not be available for proposed projects as they have not been constructed or operated yet, quite obviously, and this is often the case in an EA. Instead, we rely on predicted changes or predictions in air quality using air quality computer models to assess estimated changes in air pollution levels. There are many air dispersion models available in various jurisdictions around the world. In general, certain types of models may be more appropriate for certain situations. For example, in cases of emissions near large lakes or seas, onshore or offshore airflows may significantly impact air quality, and thus models that explicitly account for those phenomena may be required. Often, however, a regulatory agency may prescribe certain models as being acceptable. It may be useful for a proponent to suggest the air dispersion model to be used in the terms of reference and seek prior agreement from regulators or stakeholders on this choice beforehand. While it is obvious that the meteorological data to be used in the dispersion model should preferably be measured at the subject site or sites, often site-specific data is not available. Data from airport weather stations is most commonly used in lieu of site-specific data for air pollution dispersion modeling. However, these stations may or may not be situated close to the site of the proposed facility, and so one must carefully consider whether the data is appropriately representative for the site of the facility. Where available data from existing weather stations is of questionable relevance to the specific site, it may be feasible to establish a meteorological station at the site. This is especially justifiable, or perhaps should be demanded, where the project planning process takes many years to complete, affording sufficient time to collect appreciable meteorological data. The amount of data collected may be sufficient for modeling purposes or, if not of sufficient temporal length, at least could be used to verify longer data sets from other areas. Recent advances in meteorological modeling have allowed the use of model-generated meteorological data using, for example, MM5 or WRF, to allow the production of data nominally specific to a site. However, the model data itself may be subject to verification, depending on jurisdiction, by independent comparison against measured meteorological data, or just accepted as is, again dependent upon jurisdiction. In theory, distant sources of air contaminants will contribute to baseline air quality levels at locations close to the proposed project. In practice, however, it is found that only sources within a relatively short distance will cause significant variations in background levels. Beyond that distance, emissions from all non-subject sources will merge together to become evened out through turbulent mixing. One way to account for this dual nature in baseline air quality is to divide baseline air quality levels into regional and local components. This method is well established and formalized in various regulatory modeling guides and regulations around the world. The local versus regional division of baseline air quality is one of a number of methods available to estimate baseline levels. Where insufficient pre-existing data are available, or more accurate estimates of baseline air quality are required, the proponent can conduct measurements in the area surrounding the project. As with gathering site-specific meteorological data, the proponent may have sufficient time to measure pre-existing background at appropriate receptors. Likewise, reviewers may also demand that baseline air quality be measured in the area of the proposed facility for some time before the EA is conducted in order to collect sufficient data for statistically meaningful analysis. This may be addressed in the terms of reference. As pollutants from the proposed facilities, the subject sources, disperse through the air, they will add to pre-existing levels of those same pollutants present at so-called background or baseline levels that have been emitted from other sources, the non-subject sources of contaminants of potential concern. Baseline levels of air pollutants, however, are not the same at all locations. For example, closer to a non-subject source, background levels will be higher as they will be affected by emissions of COPCs from that non-subject source. A specific example would be consideration of major roadways in the area. These roadways will emit PM2.5, or fine particulate matter, for example, due to automobile exhaust and road dust. Roadways will also be emission sources of oxides of nitrogen, or NOx. Therefore, locations closer to roadways will experience higher background levels of PM2.5 and NOx, for example. In layman's terms, these may be called pre-existing hotspots. Thus, significant hotspots may exist close to these non-subject sources. If these hotspots coincide with areas of significant impact from the subject source of facility, then even higher and potentially problematic air quality levels may occur. Now we come to an important but often controversial or misunderstood requirement of impact assessments: the requirement to use conservative assumptions with any unavailable or uncertain assessment input data. I'm going to provide some commentary also on more refined alternatives to conservative assumptions, which can include probabilistic approaches and model uncertainty and sensitivity tests. To explain the appropriate methods to choose substitute data and where inappropriate choices can be made, the example of a proposed gravel pit and the attempt to estimate road dust emissions from unpaved roads within that pit will be used. A common method to predict dust emissions from roads is to use the United States Environmental Protection Agency, US EPA, AP42 emission factors. An important input variable within these equations is the silt level of the road. If a proponent is attempting to estimate road dust emissions, site-specific measurements will obviously not be available as the roads do not yet exist. Instead, the proponent must estimate or predict the silt levels in some fashion. Commonly, a proponent usually examines pre-existing data from similar operations and selects a value based on that data. For example, the AP42 document on unpaved roads presents measured values for silt content on unpaved roads in the gravel extraction, stone quarrying, and processing industries, and shows them to be variable. A value from these tables may be chosen. A key underlying principle that guides the choice of substitute data is that the choice must be made on a conservative basis. A conservative assumption or choice is one that does not underestimate the true value with a high degree of certainty. A conservative approach is necessary in air quality assessments to ensure that impacts are not underestimated. Of course, in this case, the true value of the silt levels is unknown, as we cannot measure silt levels on a road that has not yet been constructed. In any case, if we had the true value, we would use that value without bother to make conservative assumptions. In the example here, the simplest conservative approach would be to choose the highest value or value that maximizes emissions. This could also be considered a simple default approach. However, using an average value would not be considered conservative and so not acceptable for EAs. As an alternative to the conservative approach, apart from emissions estimation refinements, the proponent may have access to a large data set of silt levels, which then allows a more refined choice of input values based upon considering the frequency distribution of the silt data. The proponent may suggest an alternative to the absolute maximum value where some percentile is used, say the 95th percentile value. If the data set truly represents the conditions at the subject facility, then the 95th percentile value provides a 5% chance of underestimating the true value. Further, if more than one input variable is chosen on this basis, then the joint probability of underestimating the true air quality value is even lower, further assuring conservatism in the final air quality predictions. Such a probabilistic approach is not common in air quality assessments for EAs, unfortunately, and so it is imperative that agreement is reached on these methods to use and air quality acceptability criteria beforehand, preferably as part of the terms of reference development. In other words, for example, is a 95th percentile choice acceptable for each input variable, and to how many input variables can this be applied? An even more refined approach would be to consider a fully probabilistic approach for the uncertainty in the choice of input values. Probabilistic assessments of uncertainty in model inputs and their propagation through to model output has been the subject of many academic studies. Such uncertainty assessments are usually conducted after sensitivity studies have identified model inputs worth worrying about. In essence, the conservative approach obviates the need for a probabilistic assessment of uncertainty, as it ensures no underestimates with a high degree of certainty. The conservative approach can also be considered to be the simplest way of dealing with uncertainty in model inputs. However, providing results of an assessment on a probabilistic basis is also not usual and would require that agreement is reached on the methods to use beforehand, preferably as part of the terms of reference development. The final step is that the results of the air quality assessment in terms of predicted air quality levels could then be passed on to other effects experts. In EAs, a health impact expert frequently provides an opinion in the form of a human health risk assessment based upon the community-level exposure to contaminants of potential concern estimated by the dispersion modelling. This is especially the case where air quality guideline values, for example for PM2.5, may not be fully protective of human health. In addition, and likewise, an ecological expert could also provide an opinion in the form of an ecological risk assessment for the environmental level exposures of COPCs estimated by the modelling. So to summarize, the terms of reference should be obviously clear and comprehensive in terms of air quality elements. For air quality assessments, worst-case impacts are required to be assessed. All sources and contaminants of potential concern must be identified and assessed. It should be recognized that project emissions can vary, and that should be accounted for, and that baseline air quality can also vary and must be recognized and accounted for. And where there are no or uncertain input data, you need to use conservative assumptions or possibly pre-agreed refinements to those conservative assumptions. That is the end of the presentation. Thank you very much for listening to this. I hope you've found it useful. If you wish to have a copy of the slides or a copy of this recording, or if you have any questions about the contents of this slide, please email me at the given email address on this slide, and I'd be happy to help out in any way. Have yourselves a good day. Thank you.